Welcome everybody. Thank you very much for coming here. I don't know if Neil's here, but I thought I should say thank you to Neil for the perfect intro to this talk, seeing as he mentioned Clojure and concurrency on a number of occasions in his keynote. So who am I and what am I doing here? So my name is Paul Butcher, and I think the primary reason why I was invited was because I've recently had this book published, 7 Concurrency Models in 7 Weeks, which, as its name suggests, is all about concurrency and parallelism. I'm going to be talking twice in the conference. Today I'm going to be concentrating on Clojure specifically, and then tomorrow there's going to be a more general talk about wider aspects of concurrency, but today we're going to be concentrating on Clojure. In my spare time, this is what I do, which is probably much more fun than writing code. Now, driving around a race circuit is lots of fun. It's a particularly good way of throwing money away. If any of you have extra money that's lying around you need to get rid of, I heartily recommend motor racing. Driving around a race circuit by yourself, once you've got used to driving a racing car, actually isn't too hard. I can drive around a race circuit all day without crashing. The trouble is, of course, this isn't how it normally is. It's not normally just you on the circuit by yourself. This is how it normally is. And when you've got 20 people trying to share a race circuit, and each one of those 20 people is absolutely convinced that they're the next Ayrton Senna or Michael Schumacher, this happens. Now, this is a classic example of contention. This is what we don't want to happen in our code, and hopefully this is what we're going to be seeing today. This Clojure helps you have this and not that. So what's the problem? The problem is writing multi-threaded programming is hard. Actually, this isn't the problem. This is the problem. Writing multi-threaded programming is not hard. It's really, really hard. And if you want to see some of the examples that make it even harder than you think it is, come to the talk that I'm going to be giving tomorrow. Why is multi-threaded programming hard? Now, there are a bunch of reasons why multi-threaded programming is hard, but the key one is shared mutable data. If we could get rid of shared mutable data, pretty much all of our issues go away. And there are a lot of different approaches to concurrent and parallel programming, all of which have their merits, and all of them tackle this fundamental problem in slightly different ways. So, for example, there are message passing approaches. Now, message passing approaches, and I'm thinking here about things like actors and communicating sequential processes, they solve the problem of shared mutable data by getting rid of the sharing. You still have mutable data in an actor, you still have mutable data in a CSP program, but that mutable data isn't shared. So that's how they get around the problem. Now, that isn't what we're going to be talking about today. What we're going to be talking about today is Clojure, which is a mostly functional language. And functional languages get around the problem of shared mutable data by continuing to share it. You can still have shared data between your different threads in a functional program, but it's not mutable. And that's what makes it better from a concurrency and parallelism standpoint. Now, there are 2 key messages which I want to convey during this particular talk. One of them is about immutability. Immutability at heart is the thing that makes functional programming a good choice if you're writing concurrent and parallel code. But there's more to immutability than just that. Immutability gives us one other really interesting property, and that property is persistence. And we'll see exactly what we mean by persistence in a little while. But those are the 2 key things that I want you to take away from this talk today. Now, I'm going to start by talking about immutability. And then when we've moved on from immutability, we'll move on to persistence. But let's start with immutability. So I'm going to choose a really simple example. This is ridiculously simple, but the nice thing about a simple example is it's very easy for me to explain and for you guys to understand in the short amount of time that we have available, and it illustrates the key points that I want to get across. So I'm going to look at a really, really simple Java program that takes a bunch of numbers and sums them. Now, this is classic imperative code. We've got a mutable variable up here called ACK, and we're looping over a set of numbers, and for each one of those numbers we're adding it to our accumulator. The kind of Java code that people have been writing ever since Java existed. Now this is fine, this works absolutely no problem at all, but how are we going to take that and parallelize it? If we want to make this take advantage of the multiple cores that we've got inside our computer, really there's very little that we can do at this point. This is inherently sequential code. What I'm going to do now is I'm going to take you through constructing a Clojure equivalent of this and show you that because Clojure is functional and immutable, parallelizing this becomes trivial. Now before I get started, how many of you here are familiar with Lisp or Lisp-like languages? We've got a few people. Okay, so I'll just very quickly I'm going to give you those of you who haven't seen this a quick intro to how these things work. So what I'm going to bring up is the jargon is REPL. It stands for read eval print loop. It's basically a console where I can type Clojure code. Now Clojure is a Lisp, and Lisps have a slightly weird syntax, which if you haven't seen it before might seem a little odd, but it's not that difficult to get your head around. So the kind of thing where in an ordinary language I might type something like max 1, 2 to find the maximum of two numbers. In Clojure, what I do is I type the function, an open bracket, then the function name, and then my arguments, and it'll tell me that the max of 1 and 2 is 2. A lot of people blanch when they see this really weird way of calling a function, but it's just calling a function. There's nothing strange about it. Now Clojure has a whole range of functions built in. The one which I want to look at quickly is range. So if I say range 0 to 10, what it'll give me is it'll give me a sequence that goes from 0 up to the last number that I gave it, not including the last number that I give it. And I can play various games with that, so I can, for example, create an array with those numbers in it by saying into and then giving it an empty array, and that will give me an array with those numbers in. Now if I wanted to sum that array, actually the first thing which I can do is I can assign that to, so I can do something like def numbers, oops, I've got to give it a name. So that's given me a variable called numbers. If I wanted to sum the numbers in that array, I can use this really nice little function in Clojure called reduce. Now virtually every functional programming language will have an equivalent of this. What reduce does is it takes a sequence or an array or some other set of data and applies a function to it one element at a time, maintaining some kind of accumulator value as it goes along. So in our particular case, if we want to sum this, I can say reduce, and I pass it a function. So I'm going to define a little inline function here that takes two arguments. It takes an accumulator and a value, and I'm going to add, by using the plus function, the two values together. And if I give that numbers, then what it does is it sums all of those numbers together, and I hope it's your arithmetic is good enough to work out that the sum of the numbers 0 up to 9 is 45. Now, is that clear to everybody? Can you see what's happening there? Yeah. General nodding of heads. Now I can make this simpler actually. I can say, because I've created this little function here that's adding my numbers together. Actually, the plus function itself is already a function that adds numbers together. So I can actually just write this as reduce plus numbers, and it gives me my answer. Now, the first thing to note about this is that the functional equivalent of that. So I've got a function here of 1, 2, 3, 4, 5, 6 lines of code. Its functional equivalent is literally just that. So the first thing that functional programming gives us is it just gives us brevity. It's a hell of a lot easier to write this than it would be in an imperative language. but it gives us something far more interesting. To show you that, I'm going to create a much bigger array of numbers so that we've got something sizable for us to work with. So I'm going to say, so I've now created an array of numbers with 10 million numbers in it. Now I'm going to say time So time is a little utility function which just tells us how long something is going to take to run. And if I do that, I can see that it takes, well, in this particular case, 1,538 milliseconds. Now, actually, one of the problems with running anything at all on the JVM, and Clojure runs on the JVM, is that if I do this again, you'll see it takes a somewhat different amount of time. Oh, there you go, it takes a very different amount of time. Now, the problem with this is that the JVM is doing all sorts of weird things under our feet. It's doing on-the-fly compilation, it's doing garbage collection, and all the rest of it. Now, if you're performing micro benchmarks like this on the JVM, just running one example of a function really isn't very helpful. So it turns out there's this really nice thing built into Clojure, well, not built into Clojure, but built in Clojure, called Criterion, which runs multiple versions of a function in order to give us a much better idea about how it really performs. It's called Criterion. And if I bring that into scope, and I now say oops, that's interesting. Okay, I've done something foolish somewhere, and now I can't see require criterion, but require all. That should do it. Ah, it's not require all. There you go, that's more like it. There you go. So what this is doing is it's running that little reduce. I think it runs it 100 times in the background, and it takes an average of how long each of those things take to run, and it also measures the JVM overhead. And what it should give us after a little while, think among yourselves, is a summary of how long this actually takes to run. It always seems to take, when you're sitting watching it, as all these things do, it takes longer than you expect. Come on, quick bench. It shouldn't take that long. Well, maybe it's not 100 times. Okay, well, while that's running, okay, it didn't take this long when oh, here we go, right. Dum-de-dum-de-dum. Oh, come on, quick bench. There we go, right. So this is the interesting number. So the length of time it's taking us to run that reduce is about 122 milliseconds in total. Now, what I'm going to do next is I'm going to bring into scope a Clojure library called reducers. Now, what this is something that allows us to run this reduce that we looked at before in all sorts of interesting ways, and in particular one of the things it allows us to do is to create a parallel version of this. So I can do exactly the same thing as I did before, but using r/fold. This performs exactly the same operation, but it does it by running it in parallel across the various different cores in this machine. And if I use it'll do the same thing again. Talk among yourselves. This generally didn't seem to take this long when I did this earlier. Maybe there's some. I don't know exactly what's going on inside QuickBench. I think. Oh, here we go. Right. So. Okay. Clearly, something very strange is going on here because when I did this before, that was a much smaller number. This is the peril. These are the perils of giving real examples in talks. Because normally, what I see is a 4 times speed up when I run this. And it certainly worked okay in my hotel room this morning. Yeah. So why is it only running on one core? That's really okay. Well, this is a perfect example of how giving examples in talks. Okay, I'm genuinely confused at this point, because this has worked every other time I've ever done this, and I don't know what it is about what's going on here. That's anyway. You'll have to take my word for it, which I'm really sorry about. I don't understand what's going on here. Okay, I apologise. Normally, and I genuinely don't know what's changed this, when you use fold, the answer that comes out of QuickBench is something around 40 milliseconds. So we get about a 3 times performance speed up on my computer here, which is a 4-core machine. If anybody has any bright ideas about why it hasn't worked when I've done it this time, I'd love to hear it. And the point that I was going to make was that this is fast because Clojure is doing the parallelization behind the scenes, and the reason why it can do that is because the reduce is using immutable data. And I'm going to go, as soon as this talk is over, I'm going to go upstairs and I'm going to try and work out why this didn't work when I showed it to you now. I wonder if it's something about plugging a projector in that makes one of my cores not work, or something stupid like that. So the point is that we can just apply a slightly different version of the same function to our set of data, and it should just parallelize for us. And I apologise that it hasn't worked here. Now that's immutability. And immutability is really useful. It's a fantastic way of writing a very large number of programs, but a lot of programs are all about changing data. I mean, we genuinely want to make some change to some sort of state, whether that's in a database or whatever it might be. And there are functional languages which allow us to achieve the effect of making these kinds of long-lived state changes by using features like monads and category theory and scary things like that. One of the nice things about Clojure is that Clojure gives us a much easier way of thinking about these things by giving us something which, if you're coming from an imperative programming language like Java, feels much more familiar. And this is called an atom. There are various other things in Clojure which give us similar sorts of things, but the thing I'm going to look at to start off with is an atom. So an atom is basically a mutable variable, and I can define it like, say, if I'm my atom. So here I have an atom which I've put the integer value 0 into. I can get it by saying dref my atom, and there's a shortcut for that which is just use an @ sign. So that'll give me my number back. And if I want to change this, the way that I change it is I use this function called swap, and I pass my atom to it together with some function which I'm going to call on that. So for example, inc increments the number and I get back 1, and sure enough, if I look at my atom, I can see that it now has the value 1 in it. And I can pass additional functions to additional arguments to my function. So I can maybe say +3, and it will now add 3 to that atom.
This exclamation mark means that it has a side effect?
Almost, not quite. The meaning of the exclamation mark is actually that it's not safe to be called within a transaction in the software transactional memory implementation within Clojure, which is a very interesting topic which I'm not going to talk about here. So that's an atom which has got a number in it, but I can put a more interesting data structure into my atom. So for example, I could put a list into an atom. So I could do something like my list and give it an empty list. And then I can call methods on this, like, for example, my list. So what this will do is it'll call the conj function, and the conj function adds an element to a list, or adds an element to any data structure actually, but in this particular case it's a list. Oops, what have I got here? Because I defined my atom wrongly. It should be atom list. There we go. There we go. So it'll give me a list with a 1 in it. And similarly, I can just keep adding things to my list. Now I'm going to take a quick look at a piece of code that I've written here, which is this. Now this is a tournament server. This is something which just it's defining here an atom with an empty list in it, and this is a server which is going to allow us to maintain a list of players in some tournament. So I can find out who the players in the tournament are. I can find out I can add players to the tournament. So this is exactly what we just saw here. We've got the list. We're calling conj on the list with a player, and I can remove players from the list. Now I'm not going to explain this code in detail, but effectively, hopefully it's fairly clear that what's happening here is it's modifying the list by taking a player out of that list. And then we've got a little tiny piece of code that's going to expose this as a web service, a little RESTful web service that we can call. So let's try actually running this. So this is spinning up a little web server. There we go, and I can use curl to look at this. So I could do something like curl so it tells me to start off with that my list of players is empty. I can add a player, so I'll add a player called Paul, add a player called George. There we go, and if I now take another look, I can see that I've got my list with the different players in. Now this is all very, very, very simple. We can add John if you like, absolutely. I can even demonstrate that I can delete players. Now, this is all very, very simple. I want to look very briefly at the Java equivalent of this. So the Java equivalent of this would be something like this. So we've got a list of players, we've got an add player that adds to it, we've got a remove player that removes from it, and we've got something that allows us to get hold of the current list of players. And similarly, I've got a little piece of code here that uses this really nice Java library called Spark, which allows us to create a little RESTful server that uses that. And in just the same way as I had with the Clojure, I can spin up something that will serve that, and I'll ask you to take my word for it that if I did the same set of curls on it, it would give me the same kind of results back. Now I've got here a little program that runs a stress test on our server. And what this is going to do is it's going to create a whole bunch of players. Now, that worked. Now the reason why it worked is because I passed 1 to my stress test. Now that's saying I want you to create 1 thread to hit this server. What if I tell it to hit it with 2 threads? If I tell it to hit it with 2 threads, what we're going to see is, all sorts of really bad things happen. And if I look here, you can see our server has failed, and it's failed with concurrent modification exception. Now, quick question, can anybody see why that piece of code isn't thread safe? We've got a private variable called players. This is synchronized, that's synchronized, this is synchronized, so we're not accessing players in parallel if 2 different threads come in here. So why isn't this thread safe? Why are we getting the error?
You're iterating it at the same time.
Exactly. So the problem is our get players here is just returning the list of players. And this is being used back here where we're getting the players. It's converting that into JSON, it's iterating over that when it's outside the mutex. Now, keep that in mind, and I'm now going to go take a look at my Clojure code. So my Clojure code is basically exactly the same. I've got a set of players, which is defined as an atom. I'm getting the players, I'm adding the players, I'm removing the players. When I get the players, I just return the players. In the core, when I'm returning them, again, I'm iterating over those players outside of the protection that's given to us by the atom. But what we'll see is, if I spin up my server, wait for the server to start. So our server's started. This time if I hit it with multiple threads, now those weren't errors that shot past, this is just because we've got multiple threads running and they're outputting their values interleaved with each other. We can see we've got no errors, and sure enough, if I we can see that we've got a perfectly sensible list of players that have come out. And in fact, I can not just hit it with 2 threads, let's hit it with 10 threads. Let's really stress test this. Again, we can see that we're running multi-threaded because we've got the interleaved output, but again, no errors. So why the difference? Why is it that effectively exactly the same code written in Clojure is thread safe, whereas the Java version isn't thread safe? Now, this comes back to the second of the key messages which I wanted to talk about today, which is persistence. Now, what do I mean when I say persistence? So I'm going to go back into our Clojure REPL and show you an example of this. So let's imagine that I define some list. I'm going to call it list v1, and it's going to be a list of 3 numbers. So there we are, we've got a list which has got 3 numbers in it. If I then define a new version of that list, list v2, and I say conj list v1 4, so this gives me a new list, and it's the same as our first list with a number added to it. The key difference between the Clojure way of doing things and the Java way of doing things is that I still have list v1. In Java, if I had a variable containing some collection and I added to that collection, I would end up with a modified version of the existing collection. My variable pointing to the first collection would now have the new value in it. In Clojure, we can't make destructive edits to values. A list, although it's a collection, is still a value. It's not like Java where a collection is a reference. In Clojure, a collection is a value. I can also do things like, let's say, def list v3 is conj rest list v1. So rest list v1 is going to drop the first element from the list. I'm going to go add 5 to it, and it gives me the last 2 elements of the original list with a new one on the end. Now, what is this actually doing under the covers? What's happening in terms of what's going on inside memory? So when we define list v1, this is what we get. We get some variable pointing to a list in memory with those 3 values in it. When I define list v2, what I get is this. So list v2 points to this new list, list v1 points to the original list. The key point is this is reusing memory. So it's not like if I wanted to achieve the same effect in Java, where I'd have to copy my entire list into some new variable. If I wanted to create a new version of the list with one thing added to it, I'd need to use something like copy on write array list, or whatever it is I decide to do. In Clojure, I get this structure sharing completely for free. The second example that we gave, where we dropped one entry off the beginning and we added a new value onto the front. Again, we've got structure sharing going on here. So we're getting persistence, but we're getting efficient persistence, where it's not having to make big copies of the data that we're working with. Now, this isn't perfect. If I go back to my example again, if I was to do something like Oops. So I got a new list v1, and I do something like def list v2, like that. So list v2 is just the first two elements of the list. What that's doing under the hood is something like this. So in this instance, it is having to copy, because taking the first two elements off a list isn't something that can be done without a copy. But all data structures within Clojure are persistent. This is something that just falls out in the wash when you write data structures in an immutable language. So arrays are persistent, maps are persistent, sets are persistent, and they use really, I'm not going to talk about them here because we haven't got enough time to talk about them here, but they use really clever internal representations of these things, things called hash map array tries, which are mind-bending if you ever want to take a look at how they work. But they allow you to have things that work like arrays, so things where you can just stick something into the middle of an array, or things that work like maps where you can just take one element out of the map, put a new element into the map, and they structure share in memory, so you get memory efficiency. They also do it in such a way that the runtime performance guarantees are very similar, identical in fact in amortized terms, to the runtime performance guarantees that you get within Java if you actually go in and use mutable data structures. But they give you this really key feature, which is persistence. And because these data structures are persistent, it means that we can write this code. So this is exactly, oops, if I actually show it to you, this Clojure code is exactly as simple as the Java code that we wrote here. Well, it actually is not exactly as simple, it's simpler than the Java code that we wrote. And we're dealing with mutable data because an atom is mutable. But we do so we've got all the things that we're used to having. We can make destructive modifications to a variable, but we do it in such a way that we don't have the kinds of accidental concurrency issues that we have within Java. And this is the point that Neil was making in his talk. It just works. You write in Clojure the simple, straightforward, natural code, which is very similar to the simple, straightforward, natural code that you've been writing in Java, but it works in a way where you don't end up with weird concurrency problems. You write this code in Java, really weird shit happens, and that's to my mind at least, the key value of something like Clojure, is you're writing, as near as damn it, exactly the same code as you've been used to writing, but it all just magically works when you're operating in a concurrent environment. So does that make sense?
I have a question. You showed in the example that you have multiple different named variables.
Yes.
Remain as they were, but here actually seemingly the variable value changes because you change the same layers.
Right.
So to still remain in your own version of the layers.
It's still there. So actually, let me show you a specific example of that. If I do def my atom list 1, 2, 2. So I've forgotten to put the atom in again. So that's exactly the case we were just talking about. I've defined an atom called my atom. If I take a reference to what happens to be in that list at the moment, so I do my copy, and I make that current value of my atom. If I look at my copy, not surprising, it's got exactly the same value there. If I now change the value of my atom by doing, say, so now my atom has the value 51234, but my copy still has that old value, and that's the key difference. I've got a reference to the previous value. Anything at all can happen to my atom from now on. It doesn't matter what happens to my atom. The reference which I took will always have exactly the same value in it. And because Clojure's data structures are persistent, that's true. And that's the key difference. In Java, if I'd done the same thing, I take a reference to a variable, something else changes the variable, all of a sudden the reference that I've got, that's changed as well. That's the key difference. Make sense? Perfect.
In your stress testing example, if you modify this list at the same time, so is it possible that actually you will lose some data?
No.
Because of this copying?
No. Well, that's the point. There is no copying going on in this particular example. That's the beauty of the data structures under the hood, is that the Clojure runtime is set up in such a way that what you do looks like making a destructive update. You're actually not making a destructive update. It just looks like it's a destructive update. The previous values are always there. It is impossible for you. Well, okay, I'm not going to say impossible, because if you really try hard, I'm sure you can confuse it. But the natural code that you write, very similar to the kind of code that you would write in Java, just works. And I mean, if you've got a particular example in mind, maybe we can talk about it afterwards. But no, there is no way of losing data in this particular example. So that's pretty much it in terms of what I wanted to talk about. So as we said, the problem is shared mutable data. And the nice thing about Clojure is that Clojure gives you, if we think about, we're talking about what our, we're talking about what our other languages did. We said for things like message passing, we lost the ability to share data. In functional programming, pure functional programming, we lose the ability to mutate data. What Clojure gives us is something where we do have shared mutable data, but it's thread-safe shared mutable data where the natural way of writing code just naturally works. And that was it in terms of what I wanted to talk about. I apologise profusely for the fact that my fold example didn't work. When I work out why my fold example didn't work, I'll let you guys know. So that was it. Any questions? Yes?
What do you estimate was the biggest challenge regularly trying to Java write using dependencies?
I've been thinking about this quite a lot, actually, because my personal history is I used to work for a company called Harlequin way back in the day, and we produced a version of Lisp which we were trying to get programmers all over the world to use, and we failed. We completely failed. And at the time, we thought the reason for that was that the Lisp syntax was so strange that people who've come from a Java, C, Ruby kind of world wouldn't be able to get their head around the syntax. Actually, I've not seen that with people coming to Clojure, and I think the reason for that is that the attraction of moving to a Lisp 10, 20 years ago wasn't big enough. People couldn't see a big enough advantage in order to push over this weird syntax thing. Now I think the advantages are big enough that people are prepared to put the work in to get over the syntax. And the syntax isn't hard to get your head around. It's just a different way of thinking. So really, it's just getting your head around some of the differences about dealing with immutable data. And once you spend a little bit of time with this, it's the sort of thing where when you start, you'll look at it. How the hell can I do this without a mutable variable? But very, very quickly, you see that the number of times you need a mutable variable is very, very small indeed.
Does this syntax actually give you any benefits? You could probably do the same with another syntax.
You can, and in fact there are languages which provide the same kind of approach with a different syntax. The primary benefit of the Lisp syntax is that the jargon is it's homoiconic, so you can actually represent the syntax as a data structure within the language itself, and that allows you to write macros which are very interesting, very powerful, and I'm not going to talk about here, but there are definitely benefits to the syntax. But actually, you don't have to have this kind of syntax in order to get the sort of things that we're showing here. And in fact, there are languages. I'm thinking, for example, of things like Elixir, which runs on top of the JVM. Which runs on top of the Erlang virtual machine, rather, which gives you a lot of the same kind of features, but in a syntax which is much more Ruby-like. But yes.
How do you compare Java
Yes, and they're broadly similar. Certainly, hand-rolled Java will be slightly more efficient than something written in natural Clojure, but the difference is very small. And in my experience, the additional productivity that you get, and not just additional productivity, but the additional certainty that you get that what you've written is thread safe, massively outweighs a relatively small memory overhead for writing stuff in Clojure.
Will this big memory structure that is underneath be also efficiently garbage collected? For instance, if
Yes.
I lose pointers to some of parts of the
Yes.
structure, then there are no like internal dependencies which keep things in memory.
No, there's a huge amount of work has been put into making the internal Clojure data structures efficient for memory usage, memory reclamation, runtime, all the rest of it. Broadly speaking, the performance guarantees and the memory guarantees of a Clojure data structure are identical to the mutable Java equivalent. So you can modify an element in the middle of a Clojure vector in constant time, just like you can in Java. As near as damn it, if you expect to get a certain level of performance from the Java data structure, you'll get the same level of performance from the Clojure data structure, the difference being that it's immutable and persistent.
Well, it seems a little bit similar to, or just the most simple case is actually working with strings, which are also in Java.
Yes.
So it's quite analog.
Yes, that's a very good analogy. It's one of the interesting things about Java is that Java has got this kind of hybrid, some things are values, some things are references. What Clojure does is it makes everything a value. Okay, and I think that's us for time. So thank you very much, everybody.